Yesterday we talked about displacement reactions of metals and how those could be used to uh, identify the reactivity of metals. We also talked about identifying metal ions by adding an alkali to them, right, to a solution of their salt, and then that would produce insoluble metal hydroxide precipitates. Today, we are going to move to talking about the extraction of metals.
Okay.
Right, so we know metals are a resource found in the earth, right? So they might be mines or something, and they are usually found in most cases as ores, right? What are ores? Metal ores. Metal ores are, you know, compounds of deposits of compounds of desired metal plus impurities, so other stuff along with it that you don't want, obviously. Now, why are they present as compounds, right? These ores. And that's basically because it depends again on the reactivity of the metals. So the more reactive the metal is, right, the more quickly and easily it will react with other elements in its environment. And not only that, right, the stronger the compound formed will be in terms of its bonding. And because of that, the more difficult and therefore expensive the extraction will be. Right, so extraction means, right, getting the desired metal from the ore. And we talk about metal, we talk about the metal only. So for example, right, sodium ores. Sodium is found as sodium chloride. And we know from earlier, right, this is an ionic compound. And it has very strong bonding. And sodium is very reactive, right? So it reacts very fast. It is difficult to separate as well because it wants to stay as sodium chloride. And so, right, the very reactive metals, the process used, right, they're extracted using a process called electrolysis. Right, electrolysis is something that we will cover later on. It's actually an earlier chapter as far as the organization of the contents of the syllabus is concerned. So we'll go back to that, let's say. right? And so this is an expensive and difficult process. And one reason why it's expensive is because it utilizes electricity.
Yeah.
Right? And so the extraction process usually occurs where electricity is cheap. Right? So maybe it is somewhere where you get hydroelectric power. Okay, and this is given in the book as well. Then other, oops, where are we? Right, other metals are mixed with carbonates or oxides, right? Sorry, the ores. Uh, right, maybe mixed with carbonates or oxides or sulfides, right? And other impurities. So just a second. Other metals lower in the reactivity series, right, are reduced using uh, carbon. Right? So we know metals lose electrons when they're forming ionic compounds, and so they are in oxidized state. So when we're talking about reducing them with carbon, meaning that we're giving them the electrons back, and so they are breaking the bonding and separating the elemental metal. Okay, and we'll actually talk about the extraction process for carbon. No, sorry, not for carbon, for iron. The book also goes on to mention, right, that how effectively extraction happens depends on the concentration of the metal in the ore. So they give examples of an iron ore hematite, which has 80% of iron oxide. Other ores have much less percentages of the desired metal, and so they need to be concentrated and everything, and so large lumps are taken, crushed and processed and everything. All right, so that's some information given in the text. I'm not writing it on the board. You can read that from your books. And then you've got the metals such as gold and silver. And we know from the reactivity series that they're very chill. Right? They're the chill guys. They don't react, and so they are found in their elemental state, right? Unreacted. And so when you need to, the extraction process for these basically involves purifying them by removing impurities, so other compounds that are mixed in the ore or the deposit where gold or silver is, and right, not having to separate the gold from whatever compound it has formed in the ore. Does that make sense? Is that clear?
Yes.
Aram?
No.
Okay. There's also a table in your book, you can take a look at it, which gives you some ores for aluminum, copper, iron, sodium, and zinc, and the compound that they are found as, and also the methods that are used to separate or extract them. Now, let's talk about the extraction of iron. Right, so there are two ores of iron, hematite and magnetite. Hematite is Fe2O3, so iron 3 oxide, and magnetite is Fe3O4. Don't ask me why it is that way. It is way beyond our required understanding in the syllabus. And this is done in a blast furnace. Right? A diagrammatic representation of the entire process is given. By the way, these ores contain 60% plus iron in them, so they're rather concentrated. And the extraction takes place in a blast furnace, which is like a 50-meter high steel tower. And it is lined with heat resistant bricks. And what happens is that the ore, what's used is the ore in steps, but right, overall you've got the ore, you've got coke, and we're not talking about the soda, right? This is carbon, right? And the coke is made by heating coal. And you've got limestone, which is calcium carbonate. Calcium carbonate. Right, so the first thing that happens is that hot air is passed right from the bottom through the coke. And we know the coke is carbon. So what we're getting is you've got carbon, which is a solid, you've got oxygen, which is a gas, and you are getting CO2, which is a gas. So you're getting hot carbon dioxide. Is it balanced? Let's be quick about this.
Yeah.
Okay, it is balanced. Next up, in the heat, the limestone decomposes. And the way that's happening is the calcium carbonate, right? Decomposition means that it's not reacting, it's just breaking up. So it's breaking up into calcium oxide, which is a solid, and more CO2 gas. Is it balanced?
No.
No?
No.
Why not?
Well,
You've got one calcium, you've got one carbon, you've got three oxygens. One oxygen here, two here. So yeah, it's balanced.
yeah, okay, yeah.
Okay. The third step is that the carbon dioxide reacts with more oxygen, right, to produce carbon monoxide. Oh, sorry, not with oxygen. Carbon.
What is carbon monoxide?
Uh, just a minute. With carbon. So from the coke, because carbon dioxide reacting with more oxygen will not give you carbon monoxide at all. Okay, and this is happening higher up in the blast furnace, because remember, right, carbon dioxide is a gas and it's hot, so it will rise. Okay, and so what you have, you've got the carbon dioxide, which is a gas, you've got carbon, which is a solid, and you are getting which is a gas. This is carbon monoxide. So carbon dioxide is one carbon with two atoms of oxygen. Carbon monoxide is carbon with one atom of oxygen. Is it balanced?
No.
What do we need to do?
Oxygen needs to be two.
Where?
Haram, you wanna answer that?
Where? What do I need to do to balance this thing?
We need two oxygens.
Reactant side, product side.
Product side.
Two oxygens. I'm going to put a two over here. So now I've got
Yeah.
two oxygens and two carbons. Do I have two carbons here? Yes. Balanced. Acha, this is an endothermic reaction, right? Which means it takes in heat or energy, right? And so therefore the high temperature, hmm, high temperatures are required, because if this reaction is going to utilize heat, it needs heat in the surrounding to take in. And so the high temperature, the blast furnace is going to help this reaction move along, because it is providing the heat that it would utilize to go from carbon dioxide to carbon monoxide. Any questions?
No.
Okay. Then carbon monoxide is a reducing agent. You remember what a reducing agent is? Phobia?
Yeah.
Reducing agent definition?
It basically it reduces itself to give the other element the oxygen.
No,
I think that was oxidizing agent, right? Reducing one was it reduces itself,
no.
gains.
It is a reducing agent. It reduces something else.
Yeah.
It
To
causes the
gain
reduction of something else,
it
while
causes
itself it is oxidized,
yeah.
right? And so reduction, oxidation, just to go back to that, right? First of all, reducing agent reduces another, right? Let's say uh, element, and itself is oxidized, and so reduction, just as a recap, reduction can be the loss of oxygen, it can be the
Gain of electrons.
gain of electrons, and on the same note, it could be a reduction or actually a decrease in oxidation number. Right, there's a fourth thing as well, but I don't want to confuse you. So we haven't gone there. Oxidation, is a gain of oxygen, loss of electron,
Increase in oxidation number.
increase in oxidation number. So a reducing agent causes reduction, itself is oxidized. Okay, and so carbon monoxide is going to reduce the iron 3 oxide. And this is happening at a very high temperature, right? So 700 degrees centigrade. What does that reaction look like? You've got iron 3 oxide, Fe2O, Fe, yeah, Fe2O3. Right, you've got iron 3
So
oxide.
reduces iron 3 oxide basically means it's loss of oxygen, right?
Yes, loss
Yeah.
of oxygen, gain of electrons as well, right? All of that happening in, right? All of that's happening in this case. Uh, so this is carbon monoxide.
Like we extract iron from iron ores.
Mm, I mean, is, was that a question? I couldn't follow.
Like we extract iron from iron ores.
Yes. So iron is found as an oxide.
Like iron ores are also iron, no?
Iron is,
Iron ores are also iron or a form of iron too.
see, an ore is the element you want. The ore of an element is the element in a reacted state, right? So basically, it is a compound of that element. What you want is the pure element.
So we add more elements to get the product.
We take that ore, so we're taking that iron oxide. This is a compound of iron, and we are reacting it. We are passing it through a series of reactions. In this case, all these reactions were just the setup, right, to get carbon monoxide for this step. So it was preparation for this step. And this step, you can see you are getting pure iron, only iron, no compound of iron metal. That is the extraction. Does that clear your? Does it answer your question?
No.
Okay. Now this guy needs some balancing.
Well, carbon is balanced.
Is it?
Oxygen is not.
So you need to do something about oxygen.
Yeah. As well as. I'm gonna let you answer this one.
We need to add one more oxygen
Where?
to the product side.
Product side. So how?
Yeah.
So okay. So right, I'm putting two here. So
That
that
Yes.
makes
makes
it
the
4.
oxygen 4. So that's fine. But
Yeah.
it's making the carbon 2.
So we're gonna put carbon in 2 for the reactant side as well.
But that's going to make the oxygen 5.
Remove the 2.
Okay, I'll help you guys with this. Right? First of all, let's do the simple one. How many irons do we have? 2.
2. So we'll put 2 over there.
चलो
Yeah.
iron की तो कहानी हो गई. So iron is done.
Yeah.
Okay. Now let's take a look at carbons and oxygens. You've got 3 oxygens here, 1 here. That's 4. Right? You've got 2 over here.
We're gonna put 2. It
So
makes it 4.
yeah. So
That makes
we already tried that. Right? So how can we bring this equal to this? Now, since I already know how this works, see now what we have,
There are three.
3 and 3, so that's 6 oxygens. 3
Yeah.
times 2 is 6 oxygens, so that's good. 3 carbons, 3 carbons.
Yeah.
Can you please explain it again?
Well, the iron one is simple, right?
Yeah.
Now, because iron is balanced and there's 3 oxygens over here, you don't want to touch this oxygen because it's going to make it more messy,
Yeah.
right? And so you have one, and the carbon is fine as well. So the only problem really over here is the oxygen,
Yeah.
right? You've got 2 oxygens on the product side, you've got 4 oxygens on the reactant side. And so if initially when we put 2, so okay, fine, oxygen was balanced, but then carbon wasn't because you've got 2 carbons on the product side, 1 carbon on the reactant side. If you put 2 over here to make the carbon balanced, end up with 5 oxygens on the reactant side and 4 oxygens on the product side. So that doesn't solve anything. And so, right, maybe it's trial and error and learning, but then you try 3. And so with 3, you've got 3 carbons and 6 oxygens. Can we do something over here to balance it? You've got 3 oxygens over here. Put a 3 next to the carbon monoxide. You've got 3 carbons here, 3 oxygens here, 3 oxygens and 3 oxygens gives you a total of 6. Total 6 over here as well. And that's balanced.
Yeah.
Right? Then you have, remember you got calcium oxide,
Yeah.
right?
Yeah.
And so the impurity, right? You've got silicon 4 oxide impurities. Silicon 4 oxide, which is SiO2, right? And this is acidic in nature, right? When we, right, this uh, reacts.
What are impurities in this term?
Impurities are other compounds other than the iron compound, which is what you want to purify. There are other things that are mixed in, right? For example, right? For example, right? You're eating a toffee and it falls onto the ground, and so you got all sorts of things stuck on it. Let's say it falls into the sand. Let's keep it simple, right? So what is the thing you want? You want the toffee, right?
Yeah.
What's the extra thing that you don't want? All the sand that's stuck to it, right? So in that case, the sand is the impurity, right?
Yeah.
If you've ever seen water with maybe sand particles or something that are floating in it, maybe you right got it from, I don't know, a stream or river, or assuming somewhere, those sand particles or other particles in the water that aren't supposed to be there, those are impurities,
Yeah.
right? So this silicon 4 oxide, it reacts with calcium oxide, right, which is basic or alkaline. Again, we'll do that next chapter. And it forms calcium silicate. So the reaction for that is calcium oxide, which is a solid, and silicon 4 oxide, which is also a solid, and these two are reacting to form CaSiO3 calcium silicate, which is also a solid,
Which is also balanced.
which is also balanced. Good, right? So nothing to do over here. And this calcium silicate is called slag. Nothing to do with it. That's what it's called. Right? And so the molten, iron and the molten slag, they both trickle to the bottom of the blast furnace from where they are siphoned off, they are separated. Okay, and the slag is not useless, right? So the slag is actually used to make, among other things, roads.
Yeah.
Okay. One thing they mention over here, right? It's in the book. Usually, metal oxides are basic and non-metal oxides are acidic. So something for you to keep in mind. Right? Some oxides are neutral. Such as, so we've got calcium oxide, we've got silicon 4 oxide, carbon dioxide or carbon monoxide, so CO, and right, some are amphoteric. We came across this term yesterday as well. Amphoteric means can behave as both acid and base. An example is zinc oxide. Right, they're waste gases, so nitrogen, oxides of carbon, so carbon monoxide, carbon dioxide, and they're hot, and so they are used, the heat of these gases is used to heat up the incoming gas. So instead of using new energy to provide heat, when these gases are escaping the blast furnace, right, they're cycled close to the new gas that's coming in, which is not hot, and so there's heat transfer between the two, and so that's how the new gas is heated up. Okay.
Yeah.
All right, next up is metal corrosion. Right.
Are we gonna balance here as well?
There's not really, I don't believe there's any balancing required in this part.
Okay.
Well, yeah. No. Are you tired of balancing?
No, not really.
I mean, it should be easy,
Yeah.
easier comparatively.
Yeah.
Metal corrosion. Right. So we're going to talk about rusting. Right. And rusting is a term used specifically for the corrosion of iron. And for iron to corrode, it needs to be exposed to oxygen and water both. So if any one of these is missing, it will not rust. right? And what happens is that the iron reacts with oxygen, right, and water, and it forms a hydrated iron 3 oxide. So hydrated meaning there's water, iron 3 oxide, which is the orange, brown, right, flakes that you see sometimes. Have you ever seen rust
I guess.
on iron? Right, so what this is Fe2O3 dot H2O. Right, what does that dot mean? That means that water is present. So, right, it's not a solution. Right, it's not a solution. Water is present as part of the compound. Right, in fact, it's not just H2O, it is X H2O. Right? X could be a number. How much water is present in this, right, hydrated compound? Okay.
Yeah.
So if either water or oxygen is missing, then right, rusting is not going to happen. And they also mention, so you need both, and right, salt encourages rusting. Right, so that is why structures, especially metallic structures near the sea, rust faster.
Yeah.
Have you ever seen that happen?
I'm gonna be honest, no.
Right, and from that point we have plenty of time. I'm hoping I can complete this in today's class. We are going to talk about rust prevention. So again, keep in mind, when you're talking about rust, we are talking about iron. So rust prevention basically means preventing, right, iron coming in contact with water and oxygen. So one way of doing that is painting. That's supposed to be a 1, not a D. Painting. Right, so large structures, cars, other vehicles, they're all made of iron. Right, iron structures, vehicles, etc. They are painted with a thick coat of paint. Right, and that gives a layer, right, preventing exposure. To these guys. But right, if the paint is scratched, right, which means the iron is exposed, it will rust if the paint is not quickly renewed.
Yeah.
And that will not only rust on the spot, it will rust, the rust will spread under the paint. Why will it spread under the paint? Because now even a small spot is exposed, which means oxygen and water is getting in. Right?
Yeah.
I don't know if you've ever seen like maybe a video or something where some place is sealed and people aren't allowed to enter, and then some guy comes in and it's like, oh, open the door for me, just one guy and everything, and so they open the door slightly, and then everyone else tries to like quickly squeeze through in. I don't know if you've ever seen that happening, right, in real life or maybe a video. That's basically what's happening,
Oh, okay.
right? So even a small opening in the paint, and because the iron is being exposed, even the part that is not where the paint is not scratched, inside the iron will start to rust.
Okay.
Okay, there's an experiment in the book, right? You can take a look at it where they've placed iron nails, right, in water and air, and then dry air, and then they've put it in water with an. In fact, I'll show it to you. I'll show it to you. Can you see that?
Yeah.
Right, so what is the experiment, by the way? Right, rust on cars. You've probably seen something like that. Maybe. Okay. So, right, this is a control experiment. What's a control experiment? This is going to be an experiment against the results of this experiment are going to be used to compare with the rest. That's why it's called the control. So you've got water, you've got air. Air has oxygen, and that means these guys are going to rust. Okay. Then you've got anhydrous calcium chloride, which is a drying agent, which means this is dry air, which means there's no moisture in the air. Moisture is what? Water vapor H2O, which means there's oxygen but no water vapor, right? So the nails will not rust, right? Then you've got nails in water, but you've put a layer of oil, and that's preventing air from dissolving in water. Right? If air is not dissolving in water, and by the way, this is distilled water, not regular water. Right? What happens when you boil and distill water? Dissolved oxygen is removed. Right? So this water does not, regular water has oxygen dissolved in it. Right? Distilled water does not have any dissolved oxygen. You've put a layer of oil over here so that the oxygen in the air does not mix. And so even though the iron is getting wet, there's no oxygen for it to react. And so these guys will not rust. Right?
Yeah.
Then you've got, right, and so there's distilled water in the control as well. So why are these guys rusting? Because, well, there's water and there's oxygen in the air. Right? And then, right, this particular tube, you've got distilled water, you've got the iron nails, and you've got pure oxygen. So it's not air. And you can see by the color difference that, right, they have rusted more.
Yeah.
Right? Why? Because it's pure oxygen. So the rusting will be more intense.
Okay.
Any questions about it?
Like we don't have pure oxygen in our air or in our environment.
You don't have oxygen where?
In our pure oxygen in our environment.
Oh, no. In fact, pure oxygen is actually, I mean, unless you are, having a breathing problem or suffering from some ailment, pure oxygen can actually be harmful. Right? I mean, pure oxygen is used as a treatment in some cases, right? In some cases, but if you live in a pure oxygen environment, that will actually end up, long-term use will actually end up causing you harm. So you don't want pure oxygen in the air. Okay, going back to the whiteboard. Let's see how much I can I rush this further?
You have 15 minutes left in the meeting.
Okay. Right. Then you've got oiling and greasing. So you've probably seen that happening. Right. And so moving parts of machines, or maybe you've seen someone oiling the door or putting grease on the hinges of your car door or somewhere. Right. They are, oiled or greased, and that, makes a waterproof and airproof layer. And so that prevents rusting. Right? But because they're moving parts, right, it will get thinner and wear out over time. So you need to put more oil and grease after some time. Then there is coating with plastic. Right? And so you've got your refrigerator and your washing machine and your toaster, and all of these, they have a plastic coating outside. Right? That plastic coating, because plastic does not react with air or water. Right?
Does that include plastic containers as well?
Plastic containers, do they have iron inside them?
I know, yeah.
Well, so I mean, the plastic will not react with iron or water, but it doesn't fit this. It won't be an example for this scenario.
Okay.
Right? Plastic PVC, so polyvinyl chloride. Right? Does not react with air, and air meaning oxygen or water. Right? And so iron and steel structures. So it's a covering for, whoops, what just happened? For iron and steel. Steel is an alloy of iron, so we're just getting there. Basically, it has iron, so it fits the bill. And then there is galvanizing. Right? And galvanizing is coating iron or steel with zinc. Right? And as you know, zinc is more reactive than iron. Right? And so the coating corrodes. Right? The zinc coating corrodes, and it gives up electrons to iron. Why is it giving up electrons to iron?
Because it is a iron.
Huh?
Oh, it is a metal.
It is a metal, but why is zinc giving electrons to iron? Zinc is also a metal, iron is also a metal, right? We want to prevent
Yes.
iron from rusting.
Because iron is more reactive or zinc is more
Iron is less reactive than zinc.
because zinc is more reactive.
Acha, let's go back to rusting, right? You've got iron, you've got oxygen, you are getting Fe2O3, right? That seems balanced to me. So ठीक है? Iron oxidation state is 0. So here the oxidation state is +2, which means it is being oxidized.
It's an oxidizing agent.
Oxidizing agent की बात अभी नहीं है. It is being, iron is being oxidized.
Acha.
ठीक है?
Okay.
We're not talking about whether it's an oxidizing agent or
Hmm.
whatever. Right? Which means it is losing electrons. Right? In this in the process of rusting, iron is losing electrons.
Yeah.
Okay?
Yeah.
So to prevent this, you need to stop iron from losing electrons, which means you're stopping the reaction. Does that make sense?
Yeah.
Aram?
Yeah.
That's what's happening over here. The zinc is giving up electrons to iron. It is
To
stopping.
prevent from dusting.
It is stopping the rusting. It is preventing the rusting.
Zinc is used as a protective cover or a layer.
Yes.
for
So zinc is reacting instead of the iron.
Good job, Haram. Proud of you. Yeah.
Okay. Similar concept. Achha. They have an ionic equation. Right. So what's happening is, can I fit it in over here? I think I can. You got zinc.
Wouldn't that make it messy? But okay.
Right.
Yeah.
Okay.
Yeah.
But in fact, this is more for the next part. So actually go back on that whole thing. So bring it up again. But it's for the next part, which is sacrificial protection.
Can you cover that in here?
Hmm?
You can cover that.
I am feeling that I want to finish this. Or at least I'll stop after this. What do we have after this? Corrosion is a minor topic and alloys. They're very minor topics, but I'll leave it for next class, and then from that we'll move on to the next chapter.
Yeah.
Okay, so I will stop after this. So sacrificial protection has the same concept, right? Structures made of iron or steel, right, have bars, and by bars we don't mean like the chocolate bar size, like huge bars of zinc, right, attached to them. What kind of structures are we talking about? We're talking about oil rigs, right, and the hulls of ships, right? So those are massive structures, and so you place zinc over there, and so because zinc is more reactive, than iron, right, same concept as we just covered, right, it will react, protecting the iron, right? But what happens is, right, the zinc does get used up over time. And so it needs to be replaced or replenished, in fact. So we need to add new zinc.
Yeah.
Okay, and so the ionic equation for that is Zn plus, right, so this is solid, iron, which may be rusting, right? And so zinc is going to help, and it's going to be the one that's reacting and keeping iron as it is, as a solid. In some cases, such as underground gas and water pipes, right?
Magnesium also does
Huh?
nothing. Read.
Right? They are connected using a wire to magnesium blocks. And we know magnesium is right more reactive than other metals. You've got potassium, sodium, right? Magnesium, aluminum. Right, so the reactivity series. Yeah, sorry, potassium, sodium, calcium, magnesium, and then aluminum. So I missed calcium. Right? So it's number 4 in the reactivity series. So pretty reactive. Right? And so the concept is the same. Right? There's iron in these guys. And so the magnesium reacts giving electrons to iron, therefore protecting it from rusting. Any questions?
No.
No.
All right, so we're just near the end. Yeah, there's a bit left, but I will stop here. All right, and I'll see you guys next
Smart
class.
choice.
Huh?
Smart choice.
Yeah, time is also just up, so right. You guys enjoy the weekend. Do go through the text for this topic. All right.
Yeah, Haram was saying that she wants to leave the class early.
I think that was you at the beginning of class.
No, she messaged me. She said that sir chose a nice decision.
Huh.
Right, Haram?
No.
Yeah, she's smiling behind the camera. She definitely meant that.
You do realize this is being recorded.
Yeah.
Okay.